going to begin with 4 ways that we can represent a function. First way we can represent any function is to do so verbally, simply by using words. For example, we say that the area of a circle is a function of its radius. Virtually every area formula can be said in words, would be a verbal representation. We could also say something like the function of a parabola. Parabola is simply a function of some number squared, and so on and so on. Second way we can express functions is numerically. By numerically, we mean we can create a table of values that will show the function. So using the circle example from above, I can create a table with different radii and what the area is using that radius. For example, if I know the radius is 2, I know the area of that circle is 4 pi, and so on, and so on, and so on. Another way we can express a function is visually. Visually means we have a graph. So I can take my numeric table, or I could take my verbal description if I know what the verbal description can be pictured as, and I can create a graph out of it. So here's my visual representation. The radius is 1. This is 1 pi. The radius is 2. This is 4 pi. Each of my y values is a different multiple of pi on this graph. And I can get a representation that this appears, it appears for the moment to be an exponential function, even though it's not, because my variable is not the exponent. It could also be what looks like 1/2 of a parabola, which is more likely. Finally, we can express a function algebraically by using an explicit formula. So here I have area is a function of radius, which I called A of r, and that's equal to pi r squared. We all know what the area of a circle is. It's the radius squared times pi. 4 different ways to represent the same function. Now I could make my verbal method, my verbal model here, a little more specific. I could say the area of a circle is a function of the square of the radius, or I could just simply say it's a function of radius. Either one would be mostly accurate. Four ways to represent one function. And we need to be familiar and comfortable using all 4 throughout calculus, because we will be using all 4 at various times. The question we have to constantly ask ourselves is, for a particular function, which form is the most useful? It's not always going to be this, because some functions don't have nice, pretty formulas. Some functions, we get a better sense of them just by looking at the graph. Others, we'll get a better sense of looking at a table of values. And there are others yet that are better as just verbal descriptions, because the table of values is not readily available, or a formula would be next to impossible because the function itself is so complex. there are many functions we can describe in words that are difficult to graph or formalize. So we need to come up with, we need to basically be familiar with all four so that we can pick and choose the most appropriate one at the appropriate time. For this example, I would say the algebraic one is the most useful. It's one that we're all familiar with. Rarely do we graph area. Rarely do we use a table of values. Oftentimes we describe area verbally, but I would think the most useful for this particular example would be algebraic. Here's a function. This is a function of population. I believe it's world population for the 1900s. So here's an example where we start with a visual model. I just gave you a verbal model. It's a function of population over a given time. Could we come up with a numerical model? That'd be a little tricky because we don't have exact values. We have our y-axis right here, 5 times 10 to the 9th, but is that where this point over here is exactly? No. It's just a little bit above, and I don't have an exact value. I don't know exactly what this value is here on the scale. I know it corresponds to 1900. I know this is 1 times 10 to the 9th. I know this is 2 times 10 to the 9th. I don't know what exactly this point is here, though. And by the way, 10 to the 9th would be 1 billion. So this is not quite 2 billion. It's over 1.5 billion. But again, I don't know exactly where it is. Numerical, not the best. A formula to get all these points connected by one curve to do an algebraic model, next to impossible. So what do? Do we just say, here's the visual model and we're good? Well, we can refine it a little bit. Here's somewhat of a curve. Is it exact? No. Oftentimes with real world data, you don't get exact. You get pretty darn close. The equation for this curve right here is the lovely, this particular book calls it P of T, population, and then time. The curve there is, I'm not even going to read that number, but this is an exponential because the power is a variable. Now, is that an exact equation? It's an algebraic model, it's an algebraic representation, but is it exact? No, it doesn't go through that point, that point. In fact, it doesn't go through any of the points, pretty close to that point, but it does not pass through any of them. Is it a good approximation? Yes, it is. It's a pretty good approximation. Exact? No. But that's what you get with real world data often. You will not get exactness, and someday if you take a statistics course or several statistics courses, you'll learn about error analysis and how to minimize errors and curve fitting, try to get the best curve that's within a good enough range and all of those things. Understand here that a visual model gives us a good look at our data, a good look at our function, but to get an exact equation, an exact formula, not always possible. Can we usually get a good approximation? You bet. But we cannot always get an exact equation. Verbal model, pretty easy to get here. Numerical model, probably not possible. Although we can approximate a numerical model by plugging in values of t to get approximate values. So at, say, 1900, I would get this number. It's kind of sort of close there. 1920, that's almost right on the money. That's a pretty good approximation, and so on and so on. Here's another function. We have W, and it's in ounces, which means it's a weight. C of W, dollars, so it's some kind of cost. And this is the cost to send certain things through the mail that weigh so many ounces. This would be a numerical representation. A verbal model, just gave you one. A visual model, well, if we were to graph this, it would look like a little step or a staircase where we would have something like, well, here's C of W on the y-axis, W on the x-axis. So from 0 to 1, we would be at 32 cents. Let's say that's right here. And there we go. Add 1 from W equals 1 to 2. Now we're at 55 cents. So open circle, because I can't have 2 closed. And it also says 1 is strictly less than, not equal to. So from 1 to 2, we're at 55 cents. And so on and so on. You get the idea. There's a visual representation of this numerical data. To get an equation, to get a formula for this, we would have a piecewise function, where I would just simply take, here's our first piece, C of W is 0.32 when W is between 0 and 1, and so on down the line. It's a piecewise function. What's the best one? Probably this. If you're going to the post office, you're probably not going to see this graph. You're probably not going to see a piecewise function on the wall. You would see this little table here, this numerical representation with different weights and different prices. Got one more here. This is a graph, it's a seismograph, and it's the north-south acceleration for the North Ridge earthquake from the California Department of Mines and Geology. So here's time, and this is an acceleration scale. Now you might ask yourself, how can you have negative acceleration? Well, that just means you're accelerating backwards. So positive side on the positive y-axis, you're moving, something's accelerating forward. Negative values would mean you're going backwards. So that's why you get both positives and negatives. Can't go forward forever. At some point you got to turn around and go back the other way. And that's what the y negative values represent. So here's a little, sometimes they call them tremblers. It's a little device to measure motion. And here it's not really vibrating a whole lot. And now it's going a lot, and here it's really moving. So here's probably the most intense part of the earthquake, and then it levels off. Oftentimes, a verbal model is just describe a graph in words. That's a verbal model of a function. What do you see? Or put what you see into words. That's all a verbal model is. We started with a visual model of earthquake data. I just gave you a verbal model. How about a numerical? Probably saying to yourself, you got to be kidding. How can you make a table with all this data? Yeah, you can't really. It's next to impossible. Can you write a function to generate this curve? No, not really. Well, I shouldn't say not really. There is a technique in more advanced math called Fourier analysis that allows you to write equations that are approximations, and it uses infinite sums of sines and cosines. It is beyond anything I've ever taken, other than just I know the name of it, and that's about as far as my knowledge goes. But you could come up with a function to kind of sort of approximate this. In a way, it kind of looks sinusoidal. We've got little peaks and valleys here, then we get a big peak, big valley, and then we get a little leveling off, and then another big one, and then it sort of levels off as it goes. So I kind of sort of could do something like this. And this is kind of sinusoidal. But do I know the equation for that function? Absolutely not. Do I know a good approximation for that function? Absolutely not. If I had more expertise in Fourier analysis, could I come up with a function to approximate? Maybe. Although it would probably take me another 30 years of study to even come close to that. The point is, an algebraic model is not a good choice. A numeric model, not a good choice. This is an example. Let me get this off of here. This is an example where a visual representation is probably our best bet. So those are the different types of ways to represent functions. And again, make sure that you get a certain comfort level with all four, because they all have their uses at various times. Here's a situation that you've all experienced at least once in your life. Get into the shower, turn the water on, and you probably run out of there screaming because it's cold. Yeah, when you turn the hot water on, it's not instantly hot. Temperature, we'll call capital T, depends on the time, we'll call little t, that the water has been running. The longer you give it, the hotter the water gets. We're going to sketch a graph of this function. All we have to go on is this verbal model. The temperature of water depends on time. That's our verbal model. Is that enough to sketch a graph? Absolutely. Key word here, sketch. Sketch does not mean exact precision. Sketch means let's get a kind of sort of good enough representation. We're not looking for rulers, straight edges, very exact pictures here. Sketch is just, let's get a rough idea of what this situation looks like. I didn't want to do that. There, that's what I want. So here's an XY axis, time, temperature. Now, we don't start at 0, because when you turn the water on, water temperature is not 0. If it was, nothing would come out because it would be frozen solid. Your pipes would break, chaos would be all over your house. So no. Nor does it start way up here. When you turn the water on, it's probably, let's say, right about here. I don't know, 50-ish degrees maybe. I'm just guessing. 50-ish or so. Not really warm enough to take a nice shower. So we got to let it warm up. And as we run that hot water temperature over time is going to start to rise. Now it's at the temperature we want, so it levels off. If we let it run too long, what's going to happen? Water temperature drops because we just ran out of hot water. So now it levels off. The system has to recharge itself. And until it does that, the water temperature is going to stay down here. After a while, once the hot water heater is able to catch up, maybe it's going to start to go up again. More than likely, you would have to shut the water off and let it reheat another batch. Sooner or later, if you let it run way too long, it's going to run out of hot water and that temperature will drop back to whatever it was, possibly even a little lower than what it was, because it's got to bring in new water from the outside, from outside its storage tank. And that's typically a little colder than what was in there to begin with. So we just created a visual model based on a verbal model. Do we have exact values? No, we don't need exact values. We just need a sense of what's happening. Temperature starts here. As it heats up, the temperature rises. As time moves on, we get to the temperature we want, and it stays at that temperature until it runs out of water at that temperature, and then the water temperature drops, and that's usually a good sign that, okay, we're done with whatever we're doing because we can't stand that cold water. There's a very important word in this verbal model. Actually, there's a very important phrase. Temperature depends on time. Every single function has some quantity depending on another quantity. Something depends on time. If we were to write a formula for this function, we could call it T of X. We could call it big T of little t. Temperature depends on time. Temperature depends on time. Temperature is dependent on something. What the temperature is affected by how long this water has been running. The temperature does not affect the time. The time affects the temperature. And look where our temperature and our time were on the axis. We have two terms that you need to be very familiar with. Independent variable, we think of that as an input. We also think of it as being arbitrary. It can be anything we want it to be. There's no set value. Sometimes there's a certain set of values to choose from. In other words, we can't choose a time that's negative necessarily. So it's not entirely arbitrary, but it's not fixed either. we don't have to choose one specific value. I can choose any time value that's positive. So in that sense, it's arbitrary. And it's our domain. Independent variable is whatever our domain is. We are choosing something from our domain, and that's going to affect what our range is. Independent variable, it's the number we plug in, it's an input. And we can choose anything from that domain. And again, notice how I would write that function. Here's our independent variable right here. Our dependent variable is our y value. If we have one variable independent, we have one variable dependent. This is our output. It's not arbitrary. It's determined by something. That's why it's dependent. And it's also our range. It will be our range. So here I have a function. I just made this up. F of x is equal to x squared minus 3. Our independent variable is x. I get to choose what x is. F of x, which is also y, is our dependent variable. Y is our dependent variable. I get to choose an x value, and I get to see what y value appears. If x is 5, y is going to be 22. I don't say choose a y and then find an x. I say choose an x and then find a y. That is independent and dependent. One final problem for us to take a look at. Something you're going to have to do a lot throughout calculus. Write your own function and work with it based on some setup. We have a rectangular storage container with an open top. We're given its volume. We're also given the length of its base is twice its width. We're given costs for materials to make both the base and the sides of this box. We want the cost of materials as a function of width. In other words, my goal here is to have W, or width, be the only variable. I want one variable, and I want to be able to calculate the cost using one variable. Now we have to think about what we have here, a rectangular storage container with a volume. That's a three-dimensional shape. Three-dimensional shapes have typically three measurements. We have a length, we have a width, and we have a height. Base, we think of as its floor. Height is how tall it is from floor to ceiling. So we need to take something with three variables, pare it down to one variable. First thing you should do in a problem like this is understand you're not going to solve it in 2 seconds. You have to take it in small pieces. So let's look for some key words here. We have a volume. That's important. We have length of its base twice the width. That's important. That will allow us to eliminate one variable and write it in terms of another. Material costs, that's important. We'll come back to those. Most importantly, can we draw a box? Here's a box. If I can draw one, you can certainly draw one. We have a length, we have a width, and we have a height. And remember, the top is open. This is an open top. So there are 5 shapes being made here. We're making a floor, and we're making 4 walls. And we want W to be the only variable at the end. Right now we have 3 variables. We have a length, a width, and a height. We want to pare this down to 1 variable. And this is where all your algebra skills are going to come in handy. So here we go. First thing you need to know how to do is, how do you find the volume of a box? And then how do you find its surface area? Because these costs here are in area. That's an area, square meters. So we need to be able to work with all that stuff. Length of its base is twice its width. The length is twice the width. So I can eliminate this and say it's 2W. We've gone from 3 variables down to 2. So far, so good. Let's find its volume. Volume of a box. Its base area times its height. I was given the volume was 10 cubic meters. The base area, the area of its floor, 2W squared times its height. And this problem here is we have 2 variables right now. Right now we have 2 variables. We need to knock this down to 1 variable. Well, let's look at surface area. We can find our surface area. We can maybe go a little further. So, area of the base, 2W squared. The area of this wall and this wall, WH. And we have 2 of them. The area of this wall and this wall is 2WH. And we have 2 of those, giving us 4 WH. There's our total surface area. And I'm going to do this in a different color. Do this one in purple. Reason is that our base, materials for the floor, materials for the base, has a different cost than the sides. So I want to do this in a different color to remind myself that it's a different cost. That 2W squared is a little different cost. Right now, we have a problem. We still have too many variables. We have to eliminate one of those variables. One of those variables has to go away. Also, let's fold our costs in right now before we forget about it. So, material for the sides, $6 per square meter. Let me scroll down a little bit here. I'm going to use capital C for cost. Our total cost to create this box, here's the area of our base, and it's $10 per square meter. So when I multiply, here's how many square meters I have, 2W squared. When I multiply that by 10, total cost is 20W squared. Here I have 2WH plus 4WH That's a total of 6 WH. The total area of the sides, 6 WH times 6, because each square meter costs $6. 6 WH times 6. And there we have it. But again, our goal, write the cost of materials as a function of width. Right now I have height in there, and I don't want that. Height's got to go away. Well, let's go back to our volume here. We have our volume. We got to solve that for H. So dividing both sides by 2. Now divide both sides by W squared. And we have a formula for H. We're going to plug this into there. Cost, 20W squared, 36W multiplied by 5 over W squared. Now I have everything in terms of W, and now it's some basic algebra to solve. 36W times 5 over W squared. Like so. Now there's only one more step. Write it as a function. Right now it's not a function. Now it's a function. The cost of this box has been written as a function of width. So all we need is the width, and we can calculate the cost of making that box. Starting with a verbal model, a very intricate verbal model, and writing an algebraic function. Writing an algebraic representation of this function. Cost in terms of the width is equal to this.